All righty. Module 7, codes and standards. Let's get back into this. So we're going to review the last couple of slides, and then we're going to get rolling with the new stuff here. So if you remember from Tuesday, talked about the design process. We talked about how the electrical codes, energy codes, building standards are involved in that process. And then now we're really focusing on those codes and standards themselves. So the goals and values, you remember we looked at this slide. You know, what are really the driving factors and the reasons that these codes and standards exist? It's these things right here, right? So we talked about the differences between codes and standards. Codes are laws. They often start life as standards, as that same block of text, you know, IEC 2021, for example, ASHRAE 90.1, and then a local jurisdiction, you know, state of Colorado, city of Fort Collins, adopts that standard, adopts that document legally, and makes it a code. Codes are laws. Standards are those guidelines and the best practices, and they are official documents issued by various professional bodies, professional societies. You know, the International Code Council is one we talked about. They issue a lot of the prevailing building codes that cover all aspects of buildings, you know, plumbing, fire protection, et cetera, et cetera. So again, codes, standards, that's what they are at a very high level. We're now going to start looking at specific codes and standards that affect lighting world, lighting design, lighting installation, all of these good things here. So there we are in agenda. Codes, electrical building codes we're about to cover, so on and so forth. Getting into lighting standards there at the end. Wonderful. All right. This lovely slide, just a bunch of random electrical terms thrown up here. We're not going to worry too much about this. A couple of the ones that I did want to point out specifically and let me get my laser pointer going here again. So this is leading up to a couple slides about the NEC, National Electric Code. For those of you who have perhaps gone through engineering school, or John, electrical contractor, if you've been versed or if you've had any formal education around, you know, electrical design, electricity, circuits, that sort of thing, some of these terms would probably be familiar to you. If you are just more focused on lighting industry, then of course, voltage we're familiar with, wattage we're familiar with, amperage we're probably familiar with. And I want to quickly point out from circuits class, basically, the relationship between amps, which is current, it's electrical current, voltage, of course, 120 volts, so what we all have at our houses, 120, 208, 277, 480. Those are kind of the typical voltages in a building. Volts times amps equals watts. And I wish I had a nice little diagram here to show you. But obviously, I'm sure a lot of us understand this already. But when we are evaluating fixtures or lumen output and the wattage of that fixture, the amperage, the voltage, and the wattage all have a relationship with each other. Where a light fixture, let's call it a 100-watt light fixture, just for easy math, at 120 volts, the amperage for that is 100, let's see, V equals IR. So got to write this down real quick. My brain is not working as well as it should. 100 watts was VA. 120 volts, V equals IR. So 100 divided by 120 equals whatever that is, 0.9 amps. As you start to load up more and more of those light fixtures on the same circuit, if you had 10 100-watt fixtures, 100-watt lamps on a circuit, that would be 1,000 watts divided by 120 volts is 8.3 amps. The importance of the amperage number here, that is what drives the circuit breaker size of the circuit, and that is also what starts driving the wire size on that circuit. So just a quick little example to show you how, as you start adding wattage to a circuit, the voltage of that, the voltage on that circuit starts to affect the amperage and thus the infrastructure size, the circuit breaker size, the wiring capacity, all those things there. Let's move along here. Okay, into some specific codes and standards themselves. We'll start with the big one, the NEC, National Electric Code, also known as NFPA 70. NFPA is the National Fire Protection Association, and they are one of the bodies that issue a lot of different codes and standards that govern our buildings. Things like the electrical code, things like life safety code, things like emergency backup code. They are a body that has a lot of documentation and literature out there that tells us how to build our buildings, how to do it in a fire-safe way, and in a way that is safe to people and property. So the NEC, this book right here, gets issued every 3 years. There's a new version, and it starts its life as a standard again. Even though National Electric Code, even though code is in the name, it still starts as a standard until adopted by a state or by a jurisdiction. So you see this right here, NEC, and the actual content of this code itself, what it relates to is the installation, the design and installation of electrical systems within a building has less to do with products than it does the installation itself, the wiring, the conduits, the connections, the grounding, the bonding, the clearance requirements in front of panels, these sorts of things. And in following code and in meeting code, you are mitigating the risk of electrical fires, and you are maximizing safety to the building, fire safety, and safety to the people as well. So what are some of the provisions? What does the NEC actually say? It says a lot of things because it's 1,000+ pages, teeny tiny text, covers all sorts of things. It can be a bit of a headache if you have to go in and try to interpret it, but it has a lot of information, a lot of content. Some of that content that affects us here in the lighting world is what we have right here. Just a couple of brief examples of actual provisions from the NEC. So circuits, for example. This is kind of what I was fumbling through with my amperage, voltage, wattage anecdote earlier. The capacity of a circuit, of the wire, for example, we all have a breaker panel at home. So we all kind of know what a circuit is. Each of those 20 amp breakers or 15 amp breakers, that breaker is protecting a single circuit. There is a hot 120 volt line conductor going out to the outlets in your bedroom, and there's that neutral coming back to that same 20 amp circuit. So you have your out line and you have your neutral conductor coming back. And so that is one example of a circuit. That's a branch circuit, right? And so the capacity of that circuit is determined by that 20 amp circuit breaker right there. We can load that circuit up to an 80% of the total capacity. So 120 volts times 20 amps, which is the rating of the circuit breaker, that equals 2,400 volt amperes or watts. VA, volt amps, and watts are roughly the same thing. They're not exactly the same thing, but we're not going to worry about that. It's a whole power factor thing. John, I'm sure you are very familiar with that, outside the scope of this. But for this argument's sake, here's our 100% capacity of a single 20 amp, 120 volt circuit. We would derate by that 80% safety factor. And so we could load up that circuit to 1,920 watts worth of load. It could be light bulbs, it could be receptacles, what have you. Additional provisions of the NEC requires us to separate line voltage and low voltage conductors. So you can't run your 120 volt line voltage conductor in the same conduit as you're running a 24 volt DC signal conductor. AC and DC, you don't want those together due to the inductive capacity of that AC load. There's an electrical field literally, in the air around the alternating current lines that can induce voltages and induce currents in nearby conductors. So if you are running internet cable, Cat5 cable in the same conduit as 277 volt lighting conductors, the internet, whatever data was running on that low voltage cable, it just wouldn't work. It would see weird phantom signals. It would get a lot of induced noise due to its proximity to line voltage. So the NEC wants us to keep those separate, keep them out of the same conduit, out of the same pathway, so that they can function as intended. Accessible connections for conductors. That just means that in installing a commercial building, we need to have access, physical, literal access to panels, to junction boxes, so that electrician can come back in and service, repair, troubleshoot issues in the building after the fact. And so keeping things accessible so we can actually get to them is a big part of the NEC. Requirements on luminaires and lights themselves. They need to be physically supported from the structure. You don't want luminaires dropping on people's heads. Suitable for installed location. You can't put an indoor rated fixture on the outside. Kind of makes sense. So these are just some examples of the requirements that show up in the NEC that help lead us in the right direction to make good decisions ultimately and have the right installation, the right product for the right application. Checking in fast. Questions on the NEC. That's a whole big one. There are loads and hours and hours and hours of content on the NEC just in and of itself. Any questions so far?
None, but yeah, that means a whole course in itself.
Exactly. It's a monster. Yep. If anyone's seen the book,
it's crazy.
It's crazy. It's a big one. Yep. Makes a great paperweight. A lot of content in there too. So
it's 3 semesters at Red Rocks.
There,
good Lord.
There you go.
And you get a lot of continuing education credits.
Yep.
A lot of engineers take it.
Engineers, electricians and electrical contractors, manufacturers. There's a lot of the big ones who really need to be up to speed on the NEC. You need to know it for your profession, your PE credential, to be, apprentice, journeyman, master electrician. Got to be an expert, or at least know your way around the NEC. So that's a whole world unto itself. Some of the other, in conjunction, in tandem with the NEC, which kind of focuses on the installation of the systems, we have testing laboratories. UL is the main one, the Underwriters Laboratory. And these are more product-focused standards and listings. So while the electrical system in a building has to conform to the NEC, the products that go into that building and are installed, they have to be listed by a nationally recognized testing laboratory. UL being the big one, ETL, ETL, I have a note on what that is somewhere around here. Equipment Testing Laboratory. This is another nationally recognized testing laboratory. And UL and ETL, they exist to ensure the safety and the viability of products that we are putting into the buildings. They write standards on how those products need to perform, and then they actually test to those standards to ensure and enforce that these products do in fact pass and do in fact meet the safety requirements that they need to. So NEC for system installation, UL and ETL testing laboratories for product safety. Some other codes here. Emergency lighting, again, our friends, the NFPA. NFPA 101. This is another major code that engineers and electricians and architects and designers need to adhere to. This is life safety code. So in terms of the lighting world, lighting is a big one for life safety. Lighting is what gets people out of the building in case of an emergency, right? There are terms like the path of egress, which is kind of what it sounds like. It is a designed, a specified, and a dictated path from each and every space in that building to get out, basically get into the path of egress, get into the corridor, get into the nearest stairwell, get out the nearest exit door safely. That path has illumination requirements around it, right? So people need to be able to see if there is a fire, if there's a power outage, that is where the emergency illumination, emergency lighting, excuse me, the emergency lighting system comes into play. And NFPA 101 tells us that system has to provide an average of 1 foot candle along that path of egress, right? And a minimum of 0.1 foot candles. So designing your emergency lighting system in order to deliver this, you know, this is it's life safety, you know, in the industry. Quick little side anecdote, you know, we all have deadlines. There's a lot of pressure, and kind of in the lighting sales world, a lot of the things we can kind of like take a deep breath and be like, look, it's just lights. We're just selling lights. It's no big deal. No one's going to die. And then, of course, there's actually the life safety aspect to this. So it's a very serious thing. And it's really important that designers and electricians, owners, specifiers deliver a compliant emergency lighting and path of egress design. Get people out of the building safely. There are a couple typical power sources for this emergency lighting, right? So it can be on a generator, a diesel or natural gas powered generator. It can be with dedicated battery devices, either both in the luminaire or the frog eyes or the bug eyes. Those little dedicated, kind of ugly industrial looking devices that just sitting on the wall, they kind of look like frog eyes. There can also be an emergency inverter, which is a large battery, large centralized battery with an inverter technology, you know, to allow the DC battery voltage to power AC lights. And all of these sources, they have to provide 90 minutes minimum of backup lighting to get folks out of the building. So 90 minutes, 1 foot candle along the path of egress, 0.1 minimum. These are some requirements of NFPA 101 life safety code. Very important stuff. So those are building codes and electrical codes that we're looking at. Shifting gears a little bit over to energy codes, energy efficiency codes. You might recall from Tuesday in the lighting control section, lighting controls and energy codes go hand in hand. We wouldn't have the lighting control industry and the lighting control products and technologies that we do have without codes that require them, basically. So we looked at the control side, let's look at the code side of where all that comes from. So the two main prevailing energy codes in this country are ASHRAE 90.1. ASHRAE is, American Society of Heating, Refrigerant, and Air Conditioning Engineers, says it right here. All of these other institutes, they are all supportive in the development, the maintenance of standard 90.1. IECC, the one we were talking about, International Energy Conservation Code, that is the other main prevailing code. And there is a lot of overlap between these two. They're almost identical, in fact. Little bit of differences here and there, but for all intents and purposes, they're pretty much the same thing. There's also Title 24, which is a California specific thing. We're not going to touch too much on that here, but it is out there and we do run into it out there. So code adoption, just a quick look. Certain states, energy codes can be adopted at the state level. They are not always done that. Colorado, for example, has no statewide energy code adoption. We're one of the rare exceptions that's like that. There are certain levels where K-12 schools, for example, they're kind of managed under a certain state department. K-12 schools do have energy codes applicable to them, but the state as a whole does not necessarily. Our projects, our prevailing energy codes in this state are typically down at the actual city and municipality level. What county and what city you are installing a project in, that's what dictates the prevailing energy code. So, standard 90.1. At a high level, what does it mean? What does it require? What is it telling us to do? So it applies generally to both the interior spaces of a building as well as exterior lighting that is connected to that same building service. So that's what this code applies to. What it does not apply to is emergency lighting that is automatically off. There's these certain specific exceptions, right? And so big picture, what this slide is saying is that energy code applies in certain applications, but there are other applications, emergency lighting, dwelling units, basically apartments or condos, things like that, where the energy code just doesn't apply. It's either not reasonable or it's not feasible, or it would be unsafe in the terms of emergency lighting. So that's something to keep in mind, is that's while code applies to 95% of the spaces, there are some pretty important exceptions where it does not apply to. And knowing the exceptions is just as important as knowing the requirements of the code itself. So we're going to kind of zoom through 90.1 here. So in order to comply, this is kind of a compliance map that we're looking at here. So the mandatory requirements, lighting controls, exterior power allowance, what that means is, how many watts can you have, your total wattage for the exterior. There are also interior power allowance, which you'll see here. Exit signs are required. Then a certain level of documentation and commissioning of those systems are all mandatory requirements for 90.1. Once all those are met, you have to make a decision. And so this decision, this is basically for the interior lighting. On one hand, we can go with an actual calculation of the interior lighting power allowance. We'll get into a quick calculation here coming up. On the other hand is an energy cost budget. We'll dig into that as well. And then there are two different versions of that ILPA calculation. So we're going to look at the top to bottom, get into a little more detail in these next few slides here. So mandatory provisions, mandatory controls. This is kind of, at a broad stroke, that entire other PowerPoint that we saw on Tuesday, other presentation we went. Well, here it is coming up over here on the code side, right? So mandatory controls are showing up in both 90.1 and IECC. So if you can see one of these, we'll just look through a line real fast. Gymnasium. what does a gymnasium require per code? So lighting power density, so 0.23 watts per square foot at a room cavity ratio of 6. I don't care too much about that. Controls, what are required? So local control, that means we need to have some manual control method, a switch, a keyed switch, a button station, something like that. We're going to need, let's see, restricted to manual on, restricted to partial automatic on. So we need automatic shut off either via sensors or via time clock. And if it's sensors, then they can only come on to 50%, or it has to be vacancy mode. Vacancy mode, again, being where somebody has to turn a light on in a space. The sensors will turn it off after the fact, but they're not going to turn it on automatically. That's what vacancy mode is. Dimming, daylight harvesting is required. And then there's the full off or the scheduled off requirement. So that's kind of just reading this controls table real quick for one example. I don't think we want to spend too much time here, but if you were to do a code compliance, actually dictating code compliance for a space, and if you had to use the interior lighting power allowance method, this is for all of your luminaires, all of your lights, the total wattage of those lights. It has to be under a certain threshold. You're only allowed so many watts per square foot for a given space type. And this is the method you use to dictate how that is. Office, 0.64 watts per square foot. So if you had a 100 square foot office, 100 times 0.64 is 64 watts. So you can have no more than 64 watts of total light in your 100 square foot office. That's what this means. And space by space method. So you go through and do that exact same calculation for each space in the building, the lobby, the corridor, the restrooms, etc. Add it all up, and then you get your total power allowance. And the space by space method dictates compliance for each of those spaces. You do it for your restroom, it's under that threshold, check the box, you pass. I'm looking for the whole building. There's another slide, it's not in here, that I was expecting to see. Energy cost budget method. For really large projects, so we just talked about the space by space. That's typical for what we see. That's most projects. For really large, complicated projects, there's another way to do it. And that involves full-blown energy modelers, where there's actually a dedicated firm or a dedicated person on the design team that is running an energy model. They're the ones who are managing the energy cost budget, because they're going to be modeling the HVAC loads, the envelope loads, the total energy usage for that building. And the compliance there means that the total energy usage is less than whatever is dictated by 90.1 or IECC. So there's space by space, which is what we usually see. We see that in the form of the ComCheck compliance thing that gets put on electrical plans and on the lighting plans. ComCheck is a space by space based compliance thing, and that's what most of the cities and jurisdictions in Colorado accept for power density compliance. All right, so that was 90.1 right there. Questions on energy code. It's kind of a big one. We kind of zoom through it. Once you start working with it, that's when you really learn it. But it's out there, and if you're in the lighting world, and especially the controls world, you run into it all the time. So excellent.
Good to go.
Good to go. All righty. Aspirational standards. These are things, Chris Slaughter and kind of touched on these earlier on. and these do come up pretty often. This is things like LEED, right? And well building. These are above and beyond code. They are not required typically by a certain jurisdiction, but a certain owner, the building owner or a developer or the design team might choose to target these for various reasons, just the intrinsic value of designing a building above and beyond the bare minimum. It's a net zero building that has intrinsic value, that has intrinsic environmental value, intrinsic community value, brand value, and real estate value. There is marketing value to being able to advertise these things to your client base, whoever they may be. So there are a lot of these different aspirational standards and a lot of good reasons that a project might choose to pursue those. Energy beyond code minimum. So LEED is probably what we are all most familiar with in the terms of these aspirational standards. Leadership in energy and environmental design. And so, this was one of the original above and beyond standards that was built up to recognize this beyond code minimum design. Save more energy, have a more positive impact on the environment, use healthier materials like better carpets in your building that don't put out as many volatile organic compounds. These are all more water conservation is a big one. Views, having literal visual sight lines out of the building and more windows, promoting daylighting, promoting occupant well-being. That was kind of, these are some of the ideas that came about from LEED. And it covers a lot of different domains, not just energy, not just environmental. Quality of light is a big one that comes up in here, not too much glare, having the right color temperatures for the right spaces, that sort of thing. Some of the basic provisions of LEED. Wellness, human wellness, people wellness is another one that comes up here. So, saving energy is an admirable thing, but also being good to your people, being good to the occupants, reduce glare so you're not giving people headaches with bad lighting design. Increase the use of control so people have flexibility and they have agency in their space and able to set their lights to the levels that they want and the colors that they want when they want to do it. Again, daylighting and views is something we kind of touched on here. That's good for people. There's a lot of scientific evidence around the increase of daylight availability and access to nature. Just being able to see that has a measurable impact on your well-being. Just having more daylight as opposed to electric light in your space has a very positive impact on one's overall well-being. And so, well building, a lot of these standards came about in order to recognize those. So let's see here, folks. We're at 7:30. And I've got a couple more sections left. Yep. So I think this is going to be a good place to call it for this evening.
Yeah.
Yep. And then this will be the tri-split module, Tuesday, Thursday, and Saturday. We're going to get back into this first thing Saturday morning and wrap it up. Any last questions on any of these code standards, NEC, UL, LEED, energy code? Anything coming up for anybody?
Good to go.
I'm good.
Oh, go ahead there.
When you start to combine all these great codes, they really constrain your artistic and design aspirations.
That it can.
Big time.
It can strain a lot of things. It can strain the budget. And that's, what we all probably kind of inherently understand is that between all the code, and it's even just codes themselves can kind of butt heads and pull each other in different ways. And then you get the standards involved, and then you try to throw a budget on top of all of that. There's just so many different priorities, tugging and pulling and pushing and pulling. That it's amazing anything gets built in the first place, but it does, and we get a lot of good architecture, a lot of great design, a lot of great installations. It's pretty complex and interesting to see it all happen. Well, wonderful. Thanks as always for everyone's time. Thanks for hanging in there and getting a little more of this module 7 squeezed out of the way. We were going to get back to it, like we all know, bright and early Saturday morning out of Cooper. So hope you all have a good evening. If you do, I'll hang around for a few more minutes. I know we talked about kind of the Saturday logistics a little bit last time. But if anybody is curious, has any more questions or comments about that, I'll hang out for a few more minutes. Just let me know.
Perfect. Yeah, I think I'm good to go. I'm excited for Saturday. It'll be a good day.
Excellent. Excellent. Good stuff, Brian. Yep, looking forward to it too.
I'm good to go.
Wonderful.
Is Saturday at the same place that the first day was?
It is not. No.
Okay.
Yep.
Okay.
It's somewhere else. It's at Cooper Lighting out in Aurora. So
Okay.
check your Google Maps now, just so you have kind of a lay of the land.
Got it.
Yep.
Okay. Thank you.
Absolutely. Yep. Thank you all. Feel free to jump right off if you're all done, and hope you all have a good night.
Perfect. See you then.
Yep. Cheers.
Thanks, you too.
Yep. Thank you.
See ya.
See ya.
Bye. Thank you.
Thanks, Rebecca. We'll see you. Bye, Lynette.
All right. Thanks, Carl.
Just like that. Thank you, Cole.
Good to go.
Excellent. Glad we got. I wish I could have finished it up tonight, but it's just a lot of